Thank you for having me today. Today I'm going to talk about the neural activity and processes associated with hitting performance and psychological processes associated with hitting performance in baseball. So a lot of times when we talk about hitting performance in baseball, we talk about the physical. We have all kinds of researchers looking at biomechanics, motion capture, force plates, things like that, and we short shrift and shortchange the psychological processes going on, and there are many involved with hitting in baseball. There we go. So the first one we tend to think about is pitch perception. What kind of pitch is it? Is it a ball or a strike? What's coming my way? And that's great, and that is obviously tremendously important, but there's a lot more going on besides just looking at the pitch. You have the scouting report, the dynamics. What pitch should I expect? What are my weaknesses? What are the pitcher's weaknesses? What are my strengths? What happened the previous at bat? You have knowing the strike zone. Whether it's an umpire or a robot in the future or whatever, you have to know what was a pitch, what was a strike, learn the strike zone, learn what's going on, understand how my performance might need to adapt. And then you have what's going on in the player's head himself. What are my goals? What's the count? Should I move the runners over? What's the coach asking for? These kind of ongoing internal processes, and all of this is going on in a hitter all the time. It's not just the pitch in a vacuum. So previous research has looked at, and research presented here at the SABR Conference has looked at, seeing the pitch or pitch perception. The Servo group has looked at pitch classification. Is it a fastball? Is it a curveball? And we can look at the neural processes, neural networks, and neural activity associated with seeing different pitches and the timing of seeing those pitches. However, that leaves out all of those self-regulatory and kind of ongoing dynamic processes all the time. So we're looking at pitch perception, which is great, but we're not seeing everything else that's going on in the hitter. We're seeing how the hitter sees the pitch, but we're not seeing how the hitter sees, should I admit? Yeah. Oh, we're not seeing, oh, let me go back. So the research to date looks at this pitch perception, but it doesn't look at all these other processes that I mentioned, right? The processes involved with what's the pitcher thinking, what should I be thinking in response to this specific pitcher, what's the count, what's the coach hoping for, what's the context, what are my goals? And these larger processes, these processes that are beyond a pitch at a time, are becoming more and more important. As we know from Baseball Reference and as we just know from watching the games, hitters see more pitches every plate appearance. So more and more of these open dynamic processes, these regulatory processes, what's the count, what's the goal, what should I be doing to adapt my performance and learn from what's happened, is becoming more and more important. So these self-regulatory learning behavioral improvement processes are more and more valuable as the game evolves for hitters to see more and more pitches. So this, psychologically speaking, these processes are involved in something called self-regulation. It's basically changing or monitoring your performance to make sure you do what you want to do. I want to work better at bats. I want to swing at strikes and not swing at balls. I don't want to chase the off speed out of the zone. How do I do that? Hitters are involved in those mental gymnastics all the time and in real time, even in the batter's box. So self-regulation, again, is this internal process where you monitor your performance. You take the feedback you're given from umpires, from coaches, from whomever, from yourself even, and you change and alter your behavior to improve what you're doing. Work better at bats. Swing at my pitch, not swing at the pitcher's pitch. And the cool thing is we can look at these self-regulatory processes in real time by looking at neural activity, and we can capture that neural activity through various measures that I'm going to talk about today. So a lot is known about self-regulation, including the brain structures involved in self-regulation, one of them being this lovely brain structure here called the anterior cingulate cortex, as you can see here. Now, we can measure the anterior cingulate cortex through EEG. And EEG is a pretty basic and simple and non-invasive technology, but anterior cingulate cortex has been shown to be related with adjustments in performance, changing behavior, engaging in difficult tasks, like hitting a 97-mile-an-hour fastball, right? So we can measure the anterior cingulate cortex activity and see its neural signature through EEG. And within EEG, you have this lovely thing called event-related brain potentials, or ERPs. And I don't want to go into much of a deep dive, but literally what ERPs are is just the neural activity that's ongoing in response to a specific event. You can time capture neural activity to a pitch. You can see the neural activity in response to an umpire saying ball or strike. You can see the neural activity in response to I swung and didn't mean to swing, check swings, things like that. You can see the neural activity that's going on with all of that. And you repeat these events, or you see these events over and over, so you can clean out all the other neural activity involved with other bodily processes or movement processes, and you can look at just the neural activity associated with that event. In this case, what we're talking about is a hitter seeing pitches, a hitter responding to umpire feedback. And within those event-related brain potentials, you have specific kind of components, as we can see an example here, and these different components are associated with different cognitive functions, different cognitive processes in real time. So this is milliseconds, which is obviously tremendously important for a hitter. Hitters don't have much time to do what they do. So how do we capture this measurement? How do we measure these EEGs? We just put a cap on someone's head. It's a spandex cap, it's a swim cap in essence, and these sensors are sewn into the head. We use some salt water gel. This is a 64-channel cap like I use in my research. It takes about 15 to 20 minutes to get someone set up in the cap. So it's not much more invasive than other measurement techniques that are used to capture biomechanical data and other types of physiological data as well. So how do ERPs work? Just a little tutorial. So someone's in the cap and they're sitting in front of a computer screen. We don't have people moving when we do EEG technology or ERPs because the movements destroy the ability to capture the neural signal. So they're sitting quietly and still in front of a computer doing some task. And while they are looking at the computer and we're measuring their neural activity, in real time, we present an event. And as you can see here, there's a little marker in the file, and we can look at the neural activity immediately following that event. In this case, the event is that flashing ball on the screen. We can see here a blink is much larger in size than the neural activity because it's outside the skull, whereas the brain's inside the skull. But we can average all these trials together and look at what's going on in the brain when you see a fastball versus see a changeup. When you are told it's a ball by an umpire tells you that was a ball, or an umpire tells you that was a strike, we can look at the neural activity to each of those classes of events and see what's going on in the brain in real time when those events occurred. So I mentioned that there are a lot of components in these event-related brain potentials, and I'm going to talk about 4 of them today and just give you a brief outline. And the interesting thing is, some of this that's going to matter with how you perform to a pitch isn't even happening while the pitch is in the air. So this first component, called the feedback-related negativity, actually occurs in response to feedback. So the time point 0 here is when the umpire called ball or strike. When the umpire says that was a ball or that was a strike, and the player maybe guessed wrong, the player took a pitch that ended up being a strike, or swung at a pitch that ended up being a ball. That time point, after that umpire feedback, we see this neural activity and this feedback-related negativity. And it's associated with prediction. It's associated with expectation. If you thought that was a strike and the umpire called a ball, your brain will sound off an alarm that says, hey, you were wrong. You need to make an adjustment in your behavior. And research has shown that maybe for experts, this is a streamlined process. They don't need quite as loud of an alarm before they start to initiate adjustments in their behavior and change what they're doing and adapt and learn their performance. So you have an expectation that you know the strike zone. At that expectation gets violated, you need to adjust your behavior. And hey, I don't need to swing at those off-speed pitches. Or I should lay off that pitch, or I should be ready for that to break back over the plate. This is ongoing in real time, and this is just in response to the feedback. This isn't even what's happening during the pitch. It matters, and it changes their performance. Another component that shows up to the feedback that the umpire gives you is this Fronto-Central Positivity. And this reflects the attention given to the feedback. So an umpire calls ball or strike, or a coach tells you not to swing at that pitch or swing at that pitch. This reflects the amount of attention you're giving that. The amount of attention you give the feedback influences the ability for you to learn and improve your performance. So the larger this is, the larger it is, the more attention you're giving to that feedback. So if you thought it was a ball and the umpire says it's a strike, and you pay attention to that and use that information to learn, it's been associated with learning and better performance following that feedback. So we can see in real time how players are using feedback to improve their performance on the next pitch. and not swing at pitches they're not supposed to swing at, or swing at the pitches we want them to swing at. Now we can look at components to the pitch itself. So here at time point zero would be the actual release point of the pitch in this study. So at time point zero, the pitch is in the air going to the hitter, and the hitter sees it. And you can look at this N2 component right here. N2 has been shown to represent and reflect response inhibition. So every pitch, a player has to decide, do I swing, do I take? Is it a ball, is it a strike? Should I initiate some response, or should I lay off a response? So this is an ongoing active process in real time that every hitter has to do for every pitch. And we can see that process, that ability to inhibit the swing and stop swinging at bad pitches in real time in hitters. And the last component I just wanted to introduce before we get into our study, so again, those ball, strike, swing, take decisions. The last component is something called the N450, or medial frontal negativity, and it reflects your ability to control the conflict going on. So again, you have conflict. Should I swing? Should I take? Is it a ball or a strike? How can you adapt your decision-making and thought processes to control that conflict and perform the way you want to perform? So this reflects that proactive control process that's ongoing in real time. Again, at time point zero here would be when the pitch is released by the pitcher. So all of this is happening in hundreds of milliseconds while the pitch is in the air before you respond to the pitch. So we wanted to look at this neural activity in real time for hitters, not just how they perceive the pitch, but how they use the feedback, how they use what the information the umpire gives them to perform better. And you'll see when I get to the results that the feedback matters, pitch by pitch. They change and adapt their performance in real time, and it's not just a pitch by itself. The context beyond that matters, and we can measure it and we can capture it. So I just looked at two groups of participants. I had a group of college baseball players, and I had a group of just college students, and we'll call them the experts and the novices. And their task was simply to be in the EEG cap while they looked at pitches and make a decision about whether the pitch was a ball or a strike. And they sat in front of a computer monitor with a response pad, so we controlled their movements so we could capture their neural activity. What we did is we presented a pitch video. They had to respond while the pitch was in the air, just like they would as they were a hitter. And then after they responded, after the pitch was caught by the catcher, they got umpire feedback. They got feedback on whether the decision they made, ball or strike, was right or wrong, just like they would in a normal hitting situation. And then the next pitch was presented. So let me give you a little demonstration of what this looked like for the hitters in a second. So again, they were seated. They just had a response pad in their lap so we could quiet the body so we could measure the neural activity. If it was a ball, they hit a button with their left thumb. If it was a strike, they hit a button with their right thumb. So they received these instructions, and then they were presented with the pitch videos. So here's a demonstration of what that looked like. So the pitch videos all started from the release point. In this case, we used some virtual reality software to put them in the batter's box, so to speak. So the videos were taken from the perspective in the batter's box. They were not in the VR headset while we collected the neural data because that would interfere with the neural data. But this is a right-handed hitter seeing a right-handed pitcher. Whoop, the video did not. Let me go back. I apologize. So pitch comes. They respond while the pitch is in the air. They get feedback from the umpire. The next pitch comes. Now, I will point out that this looks like an easy task. This is extremely difficult because the pitches, we place them specifically in the shadow area, StatCast Tom Tango's shadow area of the strike zone. And if you know from looking at that data, major league level players swing 53% of the time and take 47% of the time. So it's a 50-50 kind of pitch. So we did that on purpose so that players will get sufficient positive feedback from the umpire and negative feedback from the umpire. This is a hard task. So this would just continue, and we would do it in blocks of like 50 pitches to give them a little bit of a break. But they would see the pitch, they would respond, they would get the feedback, and then the next pitch would happen. And all throughout this, at each time point, when the pitch is released, there's a marker in the file. When they respond, there's a marker. When they get the feedback, there's a marker in the file so we can look at their neural activity to each event. And here's what that looks like. So each line in here is a sensor in the cap. Like I said, there's 64 channels. Now the first thing to point out is these are blinks. This time point here, this is a blink, and this is a blink, and you can see how large they are. The neural signature of these blinks is massive because the musculature is outside the skull. So it has a much larger electrical signal than the brain inside the skull. So what we do for blinks is we mathematically identify them and component analysis them and remove them using PCA. So they're gone. So we can just look at the neural activity. And this is why we have the person sit quietly, so we don't get any interference from physical neural activity processes. But as you can see here at the bottom of the screen, we have these little markers. So this first marker was a strike. It was coded, it was a known strike pitch. But the player responded that that pitch was a ball. And then the player got feedback from the umpire, incorrect, you were wrong, that pitch was a strike, you responded a ball. And these are all coded, and we can see in real time. As you can see here, these lines are 200 milliseconds apart. So this is in real time. These events are inserted into these files where we can time lock their neural activity to what happens to them or what they do. Here's the next pitch. It was a ball, and we coded them for high, low, inside, outside, so we know that it was a ball low. They responded to a ball. They got their umpire feedback that, hey, you were correct, that was a ball. You thought it was a ball. Here's another strike. They responded it was a strike. They get feedback that they were correct. Just like in real time from an umpire in a game, you get feedback that you were right or you were wrong. And we can look at these events, event by event, average them together, and get at the neural activity to the events. But let's first start with the easy stuff, and we'll start with their performance. If we look here at, this is response accuracy or percent correct, thankfully, the players were better than the novices. So, okay, it worked. So the players were better than the novices, but it was still a hard task. They were 49% accurate. It's a 50-50 task. In real time, it's hard to discern these borderline pitches as balls or strikes. But they were significantly more accurate, and they were actually a little slower, but this was not statistically significant. And you could argue that the players were slower because they're more mechanically efficient. They know that they have more time before they have to, say, initiate a swing than a novice would, so they can take that few extra milliseconds to be sure a ball or a pitch is a strike before they kind of make their response. But this is where things start to get interesting. Now we're looking at what happens, how do they perform after they receive the feedback. So we stripped out, and we're not looking at all the pitches. Now we're looking at specifically the pitches after they got error feedback. So they were told by the umpire on the previous pitch, you were wrong. Or correct feedback, they were told by the umpire on the previous pitch that you were correct. And as you can see here, the players are obviously overall more accurate than the non-players, but you can start to see this difference. Now, this was not statistically significantly different. I think the p-value was 0.12 because we have a pretty small sample of 14 players. But you can see here that players are regulating their performance that where after they are told they are wrong, on the next pitch, they are more accurate. On the next pitch, they are showing this self-regulation. They are showing this learning, that the feedback matters. They take the feedback in, and they alter their behavior and alter their performance to do better on the next pitch. Something you don't see in the novices at all. The novices are shooting in the dark. There's almost no evidence of self-regulation in the novices. They are just flying blind. But you can start to see that hitting is not just a pitch at a time. The context matters. The feedback they get matters. And what happens from pitch to pitch depends on the feedback they get and how they use that feedback. So now we can look at the neural data, and I'll show you the messy waveforms first. This is in response to the feedback. So this time point 0 is when it flashed up on the screen that the umpire said correct or incorrect. So this isn't even during the pitch. This is to the feedback when the umpire says incorrect or the umpire says correct. The green lines are the players. The gray lines are the novices. As you can see here, there's a smaller feedback-related negativity for the players and a larger frontal-central positivity for the players compared to the novices. So I'll show this same data in a bar graph to kind of clean it up a little bit and make some conclusions on that data. So here, the feedback-related negativity, more negative is larger, so more positive is smaller. So the players have a smaller feedback-related negativity compared to the novices. And again, research has shown that more efficient learners don't need as large an alarm bell. This represents like the initiation of adjustments. So players, experts, can start to initiate change without the 5-alarm fire blaring in their ears. They can just get a small signal that says, hey, you screwed up, fix it. And they start to initiate change. Whereas the novices, their alarm bells are going haywire. They are getting huge kind of signals that you screwed up, what's going on, what's going on. And what happens is they're not able to pay attention to the feedback. So we see here the feedback, the frontal-central positivity, where positive is larger. The players are paying more attention to the feedback than the novices. The novices aren't paying attention to the feedback. Their alarm is going off, but they're not really paying attention, especially to the error feedback. When they should be paying attention, they're not. Whereas the players are paying attention to all of the feedback, as you can see here. They are using the feedback, paying attention to the feedback to initiate change and adjust their performance. Now we look at the stimulus-driven event-related potentials. Here, time point 0 is when the pitch was released. So this was when the pitch was released in the presentation that the demo that you saw. Here we have no differences in the N2 amplitude, which makes total sense. Every pitch for every person, expert or novice, they have to decide ball or strike. They have these competing responses, and they have to inhibit one to engage the other. So there's no differences, which makes complete sense. However, we do see a difference in the players, where they're showing larger, more negative here, medial frontal negativity activation. Remember, this is how they adapt and how they control the conflict that they are feeling during the performance. So larger in this case is showing that they're engaging more of these adaptation processes. They're trying to control what's going on and regulate their performance in real time to perform better. So all of this is great, and these waveforms are messy, but the real take-home comes from this next slide. So on this next slide, in the column here, in this variable column, on the rows are behavioral metrics: response time, percent correct, post-error response time, post-error percent correct. So this is after you got error feedback. What was your response time? After you got error feedback, how accurate were you? And across the top here, we have the neural data that we talked about, these ERP components: the feedback-related negativity, the fronto-central positivity, to error feedback, to correct feedback, and then we have that N2 and that medial frontal negativity. And the point here is, for the non-players, the novices, there is virtually no relationship between the neural data and the behavioral data. There's nothing related. There's nothing going on. There's no connection between their neural activity and the behavior. But for the players, literally, every one of these neural measures, including the neural measures to the feedback, not even during the pitch, is strongly correlated with how accurate they were during the task. Every one of them is strongly correlated with how accurate they were during this task. And in fact, it's virtually the entire correlation matrix here shows these strong relationships between neural activity, both to the feedback and to the pitches, and their performance, either overall or their performance following feedback, suggesting this connection, suggesting this neural activity matters and is related with their performance. It's not just pitch perception that relates to performance. It's how you process your feedback and the adjustments you make following feedback. And you can measure this activity in real time, and it is associated with performance. And we can see here on this next slide that there's a relationship between especially that attention to the feedback, that fronto-central positivity. The attention to the feedback is associated with the neural activity on the next pitch, on the next trial, during the actual pitch itself. So there's a relationship between how you process the feedback, how you regulate your performance, how you adapt to the feedback, and how you process the next pitch in real time. This layer of data matters and is associated with how you perform. So kind of walking through that data kind of more broadly in conclusion, we have this signal, this prediction error signal is associated with overall task performance, and it's also associated with your adjustments in your behavior. For experts, the smaller signal still initiates these adjustments in behavior and changes how you process a task. And the smaller signal might be reflected in more efficient and faster learning processes, as shown in other research. The fronto-central positivity, the attention you give to feedback, is associated with your task performance. The more attention you give to feedback, the better you perform. And it's also associated with how you inhibit these unwanted responses to meet your goals and respond the way you want to respond on the next pitch. Your response inhibition processes, again, for players, this response inhibition, greater inhibitory control is associated with greater response accuracy, which absolutely makes sense. The more capable you are in stopping unwanted responses, the better you're going to be at responding the way you want to. And it's also associated with and correlated with the attention you're giving to your feedback. And it's argued in some learning and self-regulatory theories that this inhibitory control might be a candidate mechanism for how learning and adaptation and self-regulation happens. And finally, this response conflict kind of detection adaptation process, your kind of ongoing proactive control during task execution, is associated with better performance, is associated with better accuracy following feedback, the learning and adaptations you engage. And it, again, might be another candidate mechanism, how you adapt to and control conflict between these forced choices. Every pitch, hitters have a forced choice. Do I swing? Do I not swing? Is it a ball? Is it a strike? What do I do? How you control that conflict is associated with performance, and how you control that conflict is also associated with how you processed the feedback you've been given by umpires, by coaches, by whomever. How are you learning? And that changes how you adapt and how you perform on the next pitch. So the implications of this is there are neural measures out there. There's been this biomechanical boom where we're measuring the physical side of hitting, rotational velocities, motion capture, force plates, K-vests, and that provides us data and objective measures of the physical where we could just look before. Now we can measure it. Well, here we have objective measures of the psychological. Here we have more you can't fake your event-related brain potentials. You can't lie to a coach about your event-related brain potentials. Yeah, I'm ready, coach. You can't make that up. So it's a more objective measure of these psychological processes captured in real time associated with your performance. So this could be an anchor point for coaches to talk with players. This could be, well, the data say this, just like it is biomechanically, just like it is with force plates and motion capture. Now we could have a psychological measure. Well, you could be paying, focus on that learn from the umpire, learn from the robot, learn from your coaches, and use that to change your performance. So you could increase the efficiency and effectiveness of player development. You can increase, change the growth curve of player development processes, engage the processes a little more deeply for coaches and scouts and trainers to have data to talk with players and have data to back up the language and conversations that are already happening. So moving forward, I'd like to obviously link this data, these neural activity data, with in-game metrics or other metrics that teams have or players have, statistics, things like that, to show that it links with maybe chase rate, walk rate, on-base percentage, things of that nature. I'd like to explore different levels of expertise. So we found this relationship for college players. Does this relationship strengthen the more expert players are? Is it an even stronger relationship for AAA major league players than it is for single-A college players? It shows that expertise is engaged in making this learning process more efficient. Well, we could maybe see if that strengthens over time and have a real true understanding of this process. Longitudinal data. Much like with biomechanical data or physiological data, you want to compare a player to himself over time and see if he's learning or getting better. So longitudinal data would be tremendous. And expanding the paradigm. We could set up the paradigm where it is a 3-2 count, bases loaded, and have repeated pitches in that context. What do you do? Are you using the attention, or are you getting frustrated? Are you not using the information made available to you, or are you checking out? And which is something I've heard coaches say to me, that I have players that if they strike out their first at bat, they're done for the day, whereas other players will continue to kind of go after it and learn and try and improve throughout the course of a game or even an at bat. And we could maybe look at that by changing the decision matrix in the process. And ultimately, future direction to look at these things, to get longitudinal data, to get layers of data at the minor league level. I'd have to establish some consultation or partnership with teams and organizations that would allow their players to be part of this process. And it's kind of a win-win, because it would make the data richer, but then also teams would have this level of data that doesn't exist. This is a level of data that's not out there that you would have on understanding your players and helping your players develop more quickly. So this is not analytics versus the human side. This is literally the analytics of the human side. This is the analytics of the psychological side. And it seems to be lacking, but it seems to be tremendously important for influencing player development and learning processes, especially at the plate. So with that, I'd like to acknowledge Illinois Wesleyan, where I work. So they've been supportive of this research, my students and colleagues, family and friends for putting up with me, SABR for the opportunity today to talk to all of you, and all of you for being here bright and early on a Sunday morning, given the context that we've had in the past few weeks, so I appreciate that. And are there any questions? Yes, sir.
In your example, when you The interval between pitches seemed to be very quick. It looked like something that you'd get from batting practice or in the course of going against a pitching machine.
Yes, sir.
But that's not what happens in a game.
Correct.
So I guess the question I have is, how do you apply the situation to those 15 to 20 seconds between one pitch and another as the batter is thinking about everything that just happened?
Yeah, exactly. This is a very kind of speeded version of real life, and that it was done more for time efficiency and a kind of experimental efficiency. You would probably argue and typically argue that what happens in that 12 to 15 seconds is this, but amplified. So it's this, but refreshed and refreshed. So in this 500 milliseconds, the players were given between the 2 seconds, they were given 2 seconds between pitches. So in that 2 seconds, they were going through these processes. Okay, the umpire called that was a ball. I thought it was a strike. I need to change my, internally. In the 15 seconds, that would happen, but it would just refresh and rehappen and re-rehappen. Also, though, to your point, it would probably be a little more complex because they might be getting feedback from someone else. So they would have multiple layers of feedback to engage, like the coach would say something, the third base coach, or a teammate would say something. But they would have to, in essence, they would have that process ongoing multiple times or in different iterations throughout that 15 to 20 second window. Yes, sir.
Yes. Could you talk about, I understand you were limited in sort of how the setup worked and what restrictions you had in movement, but how do you think it would be similar or different if you were actually able to put it on in a real game situation? And I guess part two of that is, are baseball players really better at baseball video games?
You would hope so. You would hope they would be much better at baseball video games. But the weird thing is most video games have the perspective behind the plate. So our first publication that was published last year, one of the reviewers was like, this is an umpiring task. This isn't a baseball task because we had the view from behind home plate. So in the batter's box, ideally, there would be a way to capture them in the batter's box. You could capture them without movement in the batter's box. The problem is technologically it's getting the timing marker consistently, the marker that shows when the pitch was released and the marker that shows when the feedback was initiated. We would not be able to disentangle the cognitive neural activity from the physical neural activity associated with the motion of swinging at an actual pitch. But you could have them stand still in a batter's box and kind of see pitches and do this same task in real time in a batter's box. You would just need to be able to mark the events as they occur without error, which is the nice thing about a computerized event. It sends the marker instantaneously. People have used markers that are locked to EMG activities, so you can maybe have sensors on the pitcher's arm for the release point or when the ball is released and have that marker. But for experimental control, it was the computerized task. But I would imagine that the processes would be identical. It's just a signal-to-noise ratio problem, computerized versus in the batter's box. But the processes are well-studied and across thousands of studies and hundreds of labs across the world have looked at self-regulation and looked at neural activity of this type. And it's just now that baseball is it seems to me the perfect vehicle to study this because these are real-world experts, not lab-based created experts. These are real-world experts in this very time-limited, very complex and very difficult task, and we could apply learning theory and these learning measures to make developmental processes more streamlined and efficient.